Congratulations, you are now done R7. So we're moving backwards to R6, which looks specifically at systems of equations. So this lesson is actually a review of grade 11, and so it's more like a refresher, remembering what exactly a system of equations is and how we solve them, what defines their solution. So the first part here is an activity. What I'd like you to do is individually or with a partner, you can work through these questions and just try and figure them out. You don't need to use a formula. If you figure it out a different way, just by like guess and check even, that's totally fine. But you want to solve these questions to try and figure out, okay, what's going on? How are these related to systems of equations? So you've got 1, 2, 3, 4 questions, and then you're going to do a journal entry once you are done them. Okay, so you must do those questions. So take a second, pause the video, stop what you're doing. Don't skip ahead. Take a second and look through these questions. Awesome. So you should have finished the questions above and the journal entry that goes with it, trying to figure out what on earth those questions were asking, solving for what they were asking for. All of those questions and the ones we're going to look at below are all systems of equations. This means that they are multiple equations that describe the same set of variables in different ways. The solutions, I'm just going to switch my highlighter here. The solutions are where the equations intersect. So what does that look like? Well, let's try an example together. So a farmhouse shelters 11 animals. So 11 animals. Some are goats, which I'm going to represent with a little g. Some are ducks, which I'm going to represent with a little d. Altogether, there are 34 legs. How many of each animal are there? Okay, so number of goats and number of ducks are what we're trying to figure out. So those are going to be our variables. We know that there's a total of 11 animals. So we know that 11 needs to be the total. So when we add up the number of goats and the number of ducks, we're going to get 11. Now, how many legs does a goat have? It has 4. And a duck has 2 legs. Okay, wings do not count as legs. So when we talk about 34 legs, what we're really saying is 4 legs per goat and 2 legs per duck. So we define our variables. Then we identify kind of our like ways of measure, our different ways of measuring. I'm going to use that term kind of loosely because 11 animals, it's a counting thing, so is 34, but counting and measuring are in the same family. And then step 3 is to write our equations. So now I've got 2 equations. What can I do with this? Well, there's a few different ways to solve this. I'm going to work with graphically for this particular one, just so that we can kind of get an idea of what that might look like. So on my graph, I want to graph g plus d equals 11 and 4g plus 2d equals 34. Well, those are not really easily graphable equations, so I'm going to rearrange my equations. And I want them to be in y equals mx plus b form because that's the easiest way to graph because it gives me my y-intercept and then my slope, so how I can figure out my next points. So from here, I'm going to take equation A, equation B, or we can even call it like animals and legs. So A rearranges from 11 equals G plus D to D equals 11 minus G. Now I chose D as the one that I'm going to isolate, mostly because of my other equation, L. So I'm going to be dealing with, I'm going to have to divide by 2, and 2 goes evenly into these other values. So I'm not going to be dealing with fractions. So that's why I chose to isolate D. So I've got 34 equals 4G plus 2D. So D ends up equaling 34 divided by 2 is 17 minus 2G. Now these are a little bit more graphable. So I've got, maybe I'm going to change my set of axes. I'm not going to have negative goats or negative ducks, so I'm not going to even bother. Now D is my dependent variable now, so it's going to be vertical. G is my horizontal, it's my independent. And I'm going to plot this on my graph. So I'm going to need to go all the way up to positive 17. So that's why we're making these pretty close together. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 15, 10, 5. Okay, and my other point intercept is going to be here. So this is for L and for A. And again, that's my B value here. B, 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 and B is my y-intercept. We don't remember that part. Okay, from there, we're going to be going horizontally. We're going to use our slope to figure this out. So my slope for A is -1. So I'm going to go rise is -1, run is over 1. Rise is -1, run is over 1, and so forth. And so my line is going to look like this, to the point where if I solved for it and put in that D was 0, G should be 11. So 1, 2, 3, 4, 5, 6, 7, 8, oh, not quite. 9, 10, 11. Okay, so that is A. L, my slope is -2. So for every 1 I go down, or for every 2 I go down, I go over 1. Rise over run, rise over run, rise over run. Or I could figure out my my x-intercept again by plugging in 0 for D, in which case it would be 34 divided by 4 is 8.5. So 1, 2, 3, 4, 5, 6, 7, 8.5. And again, that's why it's nice to kind of label your axes, give us a scale, so then counting is a little bit easier. You don't have to always start from 0. And we draw that line in. Oop, not quite. Maybe if I draw a line, this will be nicer. Oh dear, not quite. Okay, so that's not working. There we go. So we isolate our point and we try and decide, okay, well, what was that talking about? So 7 and 4, it looks like, or maybe it's 6 and 5. It's hard to say. Based on my not very good graph, I would say it's 7 and 4, but we can double check that by plugging these back in. So 7 goats, 4 ducks. Let's test it out. We'll plug it back into our L equation. So we check. So we've got 34 equals 4 times 7 plus 2 times 4. That gives me 28 plus 8, which gives me 36. So that doesn't work. Okay, so maybe it is 5 and 6. So let's try that. Or rather 6 and 5. So L 34 equals 4 times 6 plus 2 times 5. Gives me 24 and 10. That works. So that's my solution. So that's the flaw with solving graphically, is that you really have to be super careful. So using this scale was not ideal. What would have been better is if I had had a grid here and I had been more precise that everything was evenly spaced. Okay, so 6 and 5 is how I'm going to read that. Okay. So my solution, my final answer, I'm not done yet, is going to be that there would be 6 goats and 5 ducks. So question 2, let's work through this one. All 231 students in the math club went on a field trip. Some students rode in vans. Okay, so again, we're going to kind of go through and write down some important information. So total is 231 students. Okay, some rode in vans, which hold 7 students. Okay, and some rode in buses, which hold 25 students. How many of each type of vehicle did they use if there were a total of 15 vehicles? So you'll notice I talk about totals and then I talk about pieces. I'm going to use V for vans and B for number of buses. Okay, so one equation is that I'm going to have 231 students. That's determined by 7 kids per van and 25 per bus. My total number of vehicles is 15, and that's strictly how many vans and how many buses. So again, I've got these 2 equations. Well, another way that we can solve this is by substitution. And so we've already kind of seen this when we learned about how to test if a factor was truly a factor of a quadratic. So what I want to do is I want to isolate one variable. So in this case, I'm going to isolate v, just because substituting it in, I'm going to multiply by a smaller number. So I'm going to rearrange this to be 15 minus b equals v. But you notice we're using the same variables. We're talking about the same thing in both equations in terms of the number of s's, or students, and the number of vehicles. I'm using a capital there just to distinguish. Okay, so I've got these 2 equations. So students and vehicles. Well, I know that my vans is 15 minus b, so now I can plug that in for the number of vans in my other equation. So this is called substitution. This is our second method of solving. So we've got 231 equals 7. And instead of v, I'm going to write all of this in its place. So 15 minus b plus 25b. So then from here, I'm going to have to stretch this out. And I'm going to get 231 equals 7 times 15 is 105 minus 7b plus 25b. So I'm going to collect like terms. I'm also going to move this onto the other side by subtracting. So I'm going to get 231 equals, or not 231, but 125 equals negative 7, and 25 gets me 18b. Sorry, this is 126. 18b divided by 18, and I get 7 equals b. So I'm going to have 7 buses. I am not done the question because it asks how many of each type. So I've got 7 buses, but then I need to solve for v. I'm going to use this rearranged equation. So I'm going to go, okay, v, I know is 15 minus b, which is 15 minus 7, which gives me 8. And so my final solution is going to be that it was 8 vans and 7 buses. Third example, we're going to use our third strategy, which is called elimination. We've got Lisa's Printing Company, LLC. There are 2 kinds of printing presses. Model A can print 70 books per day. Model B can print 55 books per day. The company owns 14 total printing presses. Okay, so 14 total. And it allows them to print 905 per day. So we need to be able to write an equation for this. So I'm going to use little a and little b to help me out. Actually, I'll use capitals. Why not? So I've got a plus b needs to give me 14. And then 70 on a and 55 per b will give me a total of 905 books per day. So again, I've got my 2 equations. We're going to use elimination this time, which means I want to somehow be able to cancel out one of my variables. So I'm going to go with a, just because I like dealing with 10s instead of 5s if I can. So in order for a to be able to cancel out if we were adding or subtracting, well, first we would want one of these to switch signs. So I'm going to switch the sign of this equation. So I want it to switch signs. I also need my coefficient to be 70 for a in order for them to cancel out. So I'm going to rewrite these now as, okay, we've got 70a, 55b, and 905. Now I'm going to have negative 70a because I'm going to multiply all of this whole equation, left and right, every piece, every term, by negative 70, which means I'm also going to be dealing with negative 70b and negative 70 times 14 gives me negative 980. Now I'm going to add these together. So a's cancel out, which is what I wanted. I'm going to be left with negative 15b and a total of negative 75 on the other side. To isolate b, I'm going to divide by negative 15, which gives me 5. So I've got 5 Model B printing presses. Now I can solve for Model A using that original equation for printing presses versus books. Okay, so using P, I'm going to go A plus 5 equals 15. So A consistent variable, please, is going to be 10. So my final solution is going to be 10 model A's and 5 model B's. Okay. When you're dealing with linear systems of equations, there are 3 possible scenarios of solutions. Option 1 is that you're going to have a single intersect, and that's what we've seen in all 3 examples here. We have a defined point, a single place where they cross. If I had graphed the equations for example 2 or example 3, I would have seen a similar thing. We are always going to have a defined point. When we have parallel lines, now remember that anything is parallel if it has the same exact slope. So any parallel lines, this is one solution for not parallel but not perpendicular, or not parallel lines. So we've got one solution for most of our systems. But if they are parallel, then we have 0 solutions because they will never ever cross. Our third situation is when we not only have parallel lines, but we also have equal intercepts. This defines equivalent lines because y equals mx plus b, the only 2 things we can alter about an equation are our slope and intercept. So if they're both exactly the same, my whole equation is the same. In this scenario, they actually overlap. That's what we're seeing here. And so what we say is that we have infinite solutions, because literally every point, no matter what value you plugged in, whether it's a decimal, an irrational number, whatever, you are always going to be overlapping because they are the exact same line. So that's the end of our lesson. You've got some practice questions to do just to kind of refresh your memory on how to solve a system of equations. So we've got 3 strategies. We can do it graphically, in which case I recommend you use Desmos, but also practice graphing linear equations. So maybe grab some grid paper. We've got substitution, and we've got elimination. But no matter which method you choose, you will always get the same answer because we were talking about a system of equations where the definition of its solution is where they cross, where we get matching values that plug into both equations. So we saw that in our first example, how we were able to check to see if it worked in my one equation. I could have checked in both equations, and that's how I knew it was 7 and 4 or 6 and 5, because it needed to satisfy that first equation. And then I had to check the second equation as well to make sure it satisfied both. Okay, so no matter what, when you plug those values into both equations that you write, they should give you like a correct answer. They should be able to fulfill that equation. So give it a shot for some practice, and then you can move on to looking at systems where we have quadratics.